So there was a request for somebody who asked me to talk about power, or actually what they asked for was, did any of the groups have their discussion on power recorded? And it turns out the answer is no. So just for kind of a special one-off for 2021, just a little talk on power. I'm using the same slides as you've seen elsewhere, so I'm going to skip over the bits that were in the other video and focus on the power side. So there was a stuff about significance. Like I said, I'm talking about this. We talked about effect sizes, and I really hope you get these concepts down. They are really important, which is why we kind of use this week to go over them. So in correlations, the effect size is R itself. In t-tests, the t isn't an effect size, so we have to work out a new one. And of course, there's the spreadsheet I designed to do that, so hopefully using that for your assignments. This is kind of basically the way it works, and the thresholds that we use for Cohen's d, and the idea that when you have two groups measured on a certain on a certain scale, intelligence or happiness or whatever it happens to be, that what d expresses is the number of standard deviations that one is higher than the other. So if it's a big difference, then the d is higher, and you can see that it's a more important, a larger effect in the experiment than a small. So power, this is the stuff that I did want to get to. So the basic idea behind power is that just like with significance, there is always a chance that you're going to find something that doesn't exist, and you're going to end up making what we call a type 1 error. There's also the chance that you can make a type 2 error, that something does exist but we can't find it, that we don't find it. All right, and the way that we combat this is to make sure that our tests are powerful enough to detect these significant effects where they exist. I mean, if the thing that we're looking for doesn't exist, the most powerful test in the world won't detect it because it's just not there, right? But if your test isn't very powerful and the thing that you're looking for is there, then you might miss it. And obviously that's a big issue. So this is about being able to reject the null hypothesis when it's false. Power there's no kind of statistical letter for power that I'm aware of, but it's measured, it's a coefficient, right? So it's measured on a scale from 0 to 1, where 0 is absolutely no power, so you'll never find anything even if it exists, and 1 is completely 100% powerful, it'll always find, it'll never fail, right? And the way that we kind of interpret this is that times that by 10 and you get a percentage, right? Because this is how we express percentages in statistics. So if your test has a power of 0.1, then there's only a 10% chance that if there is something to find, that you'll find it, right? So, you know, why bother doing it? You know, that you've only got a 1 in 10 chance of finding it. At 0.7, though, things start to look a bit better. At 0.7, there's a 70% chance that whatever effect is there, you'll detect it. Usually it's at 0.8, and I don't know why this isn't on this slide. It really should be. Usually it's 0.8 that we say is kind of the threshold for where we consider power is acceptable. Yeah, and it can get higher. 0.9 and higher like that. It doesn't often happen in psychology. It can, and you know, it's determined by all sorts of things. Let's look at the things that do determine power, because that's really important. The first thing is the size of the effect. And the basic idea behind this is that if you're looking for something that's really blatant and in your face, you don't actually need that powerful a test to find it, right? However, if you're looking for something that's kind of subtle and harder to detect, then you need a much more powerful test in order to find that. So the size of the effect that we're looking for is really important. I think what I should say now is that in order to increase power, what we do is we recruit more people to the study. So the more people there are, the more participants we have in the study, the more powerful that test is. So if you've got something really, really blatant, let's take the old example because everyone understands the metrics of this. Let's take an intelligence test, right? So we know that normally the mean is 100 and the standard deviation is 15 for IQ, and you've developed a new wonder drug and it's really, really powerful, right? And it jumps people up by 20 IQ points, right? So having said that the standard deviation for intelligence is 15, a jump of 20 is greater than one standard deviation above the mean, right? So that's a huge difference. In terms of Cohen's d, when we talk about how big an effect is that, that is much bigger than the cutoff for what we consider a large effect, which is 0.8. And I don't know off the top of my head what 0.8 of 15 is, but I'm guessing it's about kind of 12-ish, something like that. So if a jump of 12 points is considered large, a jump of 20 points is massive, right? So this isn't a subtle thing. So actually, if you did quite a small study with a small number of participants, you'd be able to detect that. However, if the drug you developed only pushed people up by about, let's say, 3 or 4 points, right? So that's going to be in the realm of what we'd consider a small effect size. Remember, people vary in all sorts of other ways. So there's all sorts of things that impinge on their ability to perform well on the test. And the effect of the drug, which is the one thing that we want to focus on, that kind of gets drowned out in all the noise of the other things. When the effect size is huge, there's no possibility of drowning that out. When the effect size is small, all sorts of other things, you know, noise and confounds and extraneous variables can get in the way of detecting that rather subtle effect. And so what we need is a more powerful test. So we need to recruit more people, and literally sometimes hundreds of people, into each condition of the test in order to get a good crack at detecting that effect, should it exist. Okay, so that's why the size of the effect is important, and it really is the thing that's most important. I guess the one thing that I haven't said is how do we guess the size of the effect? How do we know the size of the effect before we've run the experiment? And you know, that's totally a valid question. And the answer is that either you just take a wild guess, or more sensibly, you look at the literature that's looking at the same topic, or if there's nothing on that exact topic, on similar topics, right? So you might look at all the things that people have done around the world on other superdrugs, right? And how they've impacted intelligence. Now, you think that your superdrug's better than them, but if you find that all of them kind of end up with an effect size of 0.3 or 0.4 or 0.5, then it would be madness to assume that yours is going to have a 1.2 effect size. Even if you do think it's going to be better, that would be far too large, right? So you'd probably base your power calculation on an effect size of around 0.5 or something like that. There is still a certain amount of guesswork, but you've got to start somewhere really, and that's how it works. So the other thing that affects this is the significance level that you set. Now you'll see when you look at these these examples, like the AI power calculation or the sample size calculator that I've linked to in the workshop resources for this week, that they ask you to set the significance level. But actually within psychology, we've already got the significance level set, so it's P.05. Sometimes you see it written as the significance level is 0.95, but you know, 0.05 plus 0.95 equals 1, so they're just kind of the opposites of each other. So we tend not to mess with that, we just leave it as it is. The number of participants, this is obviously the big thing, and this is the one thing that, you know, we can actually change if we need to. And the type of the statistical test in two ways, like correlations and t-tests and things are worked out differently, but actually the design of the statistical test is also important. Whether it's within or between participants really matters. Within participants' designs are inherently more powerful. They require half as many people to have the same power as a between participants design. They're also generally kind of trickier to run. The other thing to think about is whether the hypothesis is one or two-tailed. One-tailed hypotheses are more powerful, but it's like with your usual hypothesis for when you're looking at your t-test and what have you. Can you justify using a one-tailed hypothesis? Because kind of the standard is a two-tailed hypothesis, right? That there'll be some effect. You need to go the extra step to justify whether that effect is going to be in a particular direction. So if you've got a drug and maybe you've got some pilot data, right, and you know that all your you know, the animals, the mice that you first trialed it on, they were all more intelligent and none of them were less intelligent after the use of the drug. So that might be good evidence for a one-tailed hypothesis, right? But again, more likely you'll turn to the literature and look at other studies that have done similar things. So if you're looking at this superdrug, you look at everything else, and actually you find that some of the drugs had an unintended consequence where actually some of the participants ended up less intelligent at the start, then it would be really difficult to justify using a one-tailed calculation here. You'd have to use the two-tailed calculation. And so when should you estimate the power of your study? And that's the, oh, those are the words that I'm missing on that screen. So really the way that you should be doing it is in order to calculate the number of participants that you need. And in fact, this sample size calculation is vital, and most good journals will insist, if you're suggesting a study that you want to do, that you do proper participant sample size calculations, right? And I've left links to a couple of these. Now, you haven't been taught this in time to do this for your study, although you might be in the middle of data collection now. So actually, you might go, oh, the minimum we're supposed to have for this study is 5 participants each, so maybe that's 20 participants in our study overall. But we did a power calculation or a sample size calculation, and it says we should have 30 people in each of our groups. Let's keep collecting data. Because remember, if you just go with a bare minimum that meets the basic requirements for being able to submit it for 1006, then you might end up with a really underpowered study, and you'll simply not find the thing that you think is there, even if it is there. The practical thing of this, actually, it's more difficult to write a paper when you don't support your hypothesis. It's not the end of the world, and you can still get a good mark on a paper like that, but generally it's a little trickier. The other thing that you can do this, the other way that you can do this is you can do it post hoc, right? So if you've done this, maybe by the time you see this video, you've already collected your data, or you read the bit, or your tutor told you that actually power calculations aren't mandatory for this assignment, and let's be clear, they're not. This is so late in the year that it can't be mandatory, so this is kind of a bonus. And you've decided they're not mandatory, so you're not going to do them. But you don't support your findings. Your hypothesis doesn't get supported when you run your t-test, and that confuses you because you're fairly confident the thing you're looking for should be there. So why isn't it? So you start to think about, oh well, maybe it's the fact that it was done online. Maybe this doesn't work very well online, or maybe it's that it's only done with students at a very stressful time of year, and maybe that's impacted. There's various things that it could be. But of course, the one big glaring thing that it could be is that you could have just simply had an underpowered study and not had enough participants. And so if you do a post hoc power calculation, so you put in, instead of putting in the effect size you're expecting and all of that, and getting out the number of participants that so if you're doing this while you're planning, you put in the power that you want and the effect size you think you're going to get, and you get out the number of participants that you need. If you do this post hoc, you put in the number of participants that you had and the effect size that you detected, and what you get out is the power level you achieved, right? And if you've not done enough in terms of data collection, then that power level is going to be below 0.8, and it may be a lot below 0.8, right? And in that case, you have an underpowered study. Now, in the real world, that's a bit of a disaster. Nobody's really going to publish that or anything. But in the context of 1006, look, that's fine. Like I said, this power stuff isn't mandatory. But what it does give you is it does give you a good way to reflect on the limitations of the study. So quite often people say, well, maybe we didn't recruit enough participants. Actually, this lets you nail it down. We know we didn't recruit enough participants because the achieved power level of this was 0.4 or whatever it happens to be, which means that it's quite likely that had there been an effect, we wouldn't have detected it. And you don't need to say anything more than that. That's one or two sentences as a part of the limitations of the study will show that you understand the notion of power and you understand how it's applied. Even if you didn't do sample size calculations, it's going to look really good. So you'll probably have seen that there are some links on this slide. Rather than edit the slide, I just put this great big stamp over it. The updated links are in the folder on Nile under week 26, I think. Anyway, the week where we did power, the second of the 3 in the final block, and more than that, you can Google for some, right? Some of them use slightly different terminologies and they can be a little confusing. So I've tried to choose, I think I've just chosen 2 this year that are kind of clear. A lot of these links on this page are, where are they? Up that direction. They're not great anymore. They've changed and the links are broken, or they use kind of peculiar terms. That's just the internet, that happens. But Google sample size calculator and you'll find a bunch of them. All right, I think I'm done. I'm not sure that I've got anything else to say about power. Just to finish off, if you've got questions about this, of course, please do use the practical report forum, and your tutor or myself or someone will answer questions there. All right, thanks.